The last result we're going to prove in this section is called the monotone convergence theorem, and it's a really important result, especially when we get to series, because when we start dealing with infinite series, it's going to be sort of the initial thing we rely on when we want to show that a series converges, even if we don't know what it converges to. Right? So that can be kind of a tricky thing, right? To show something converges without knowing what the actual value is. But this is the theorem we're going to use to get that sort of result established. And so we're going to use the axiom of completeness to prove the monotone convergence theorem. All right, so the theorem says that if you have a sequence that you know is bounded and monotonic, then the sequence has to converge. So we're going to start off with a sequence that we assume to be bounded and monotonic, and then we have to produce, right, the limit of that sequence and show that the sequence converges to it. Now, monotonic means either increasing or decreasing. Without loss of generality, we can pick one. Right? So I'm going to say, I don't know if you've seen this abbreviation, WALOG. Without loss of generality, we're going to assume that A sub n is increasing. Okay, so the proof would look very much the same if we assumed it was decreasing. Right? So we'll just assume that A sub n is increasing. We know that it's bounded, and so by the axiom of completeness, the set made up of all of the elements in the sequence has a least upper bound. So let's let L be the least upper bound or supremum of the members of the sequence. Right? We have a set of real numbers. We assume that the sequence is bounded, so we have a bounded set of real numbers. And because it's bounded, we know that there must be a least upper bound. So our claim is that that least upper bound is actually the limit. Right? So claim A sub n converges to that L. All right, so if given any epsilon bigger than 0, we have to produce a capital N so that if we go that far out into the sequence, we're within epsilon of L. So let's start with an epsilon. Right, and so here's sort of the crux of the proof. We know, because L is a least upper bound, that L minus epsilon is not an upper bound, right? L minus epsilon is smaller than L no matter what epsilon we choose, and so L minus epsilon can't be an upper bound when L is the least of all upper bounds. Right, so then L minus epsilon is not an upper bound for A sub n. But if it isn't an upper bound, that means there's at least one of these points, one of these A sub n's, that's larger than L minus epsilon. Right? So let's call that capital N. All right, so there exists capital N such that A sub n is larger than L minus epsilon. Now we can say a little bit more than that, because not only do we know that A sub capital N is bigger than L minus epsilon, it's also still smaller than L, right? Because L is an upper bound for the sequence. Now this is pretty much it, right? We've used the fact that A sub n is bounded. Now we bring in the second hypothesis that A sub n is increasing. See, once we have an a sub n bigger than L minus epsilon, because a sub n is an increasing sequence, everything else past it is larger than that a sub n and smaller than L. Right. So then n minus capital N implies every member of the sequence past capital N, right, past the term that we know is there, all the rest of them have to be in there as well. But being between L minus epsilon and L is exactly what we need for a sub n to be within epsilon of L. So that happens since a sub n is increasing. And that is equivalent to saying, or I shouldn't say equivalent, it implies that a sub n minus L is less than epsilon, right? Because the a sub n is between L minus epsilon and L. So that completes the proof. Now, just a quick sort of geometric version. Right, we've got some increasing sequence. It's bounded, so it's got a least upper bound, capital L. And we take L minus epsilon. Now this would extend to L plus epsilon, even though we don't need that. So anything in this interval is within epsilon of L. And because L is the least upper bound, L minus epsilon is not an upper bound, so there has to be a member of the sequence in there. If there wasn't, then L minus epsilon would be an upper bound. Right. Well, if X lands in that interval, then all the rest of the members of the sequence are in there also, because the sequence has to increase. And that gives us a capital N past which we are stuck within epsilon of capital L, and that completes the proof.